Now let's introduce a simple engineering example of a linear system of equations. I realize this may be outside of the expertise and interest of some of you, but it's a good motivating example, and I'll derive some simple rules you can follow to see how this analysis is done. We're going to look at simple truss analysis. Here I have a foundation and a wall. The wall is supporting some beams, which through pin joints are supporting more beams. This whole thing is called a truss structure. The purpose of the truss is to support an external force. The goal of analysis is to understand what subsequent forces are imposed within each of the beams. We'll see how to do that in a very simple case. For the elementary analysis that we're going to undertake, we have to consider only things that are called simple truss members. And simple truss members are beams that are held together with pin joints. Here's a beam and another beam and a pin. The idealization you want to think about is there's no welding. Simply line the holes up and push the pin through. So it looks like that. Okay, let's begin to see how would we analyze this. Here's a picture of the end of two beams that have been attached together by a pin and an external load P. The manner in which we model this is that the pin is what transfers all the force. The external load acts on the pin, and the pin is pushing against the two beams. Newton's third law, of course, holds, so when the pin exerts a force on the blue beam exerts an equal and opposite force on the pin. Same thing for the brown beam. Let's break this interconnection apart and draw free body diagrams of each piece. The pin is interacting with beam 1 and exerts a force on it in some direction. Here I've drawn it as shown, and I've indicated it with a brown arrow. Well, first, by Newton's third law, the force that the pin exerted on the beam is equal and opposite to the force that the beam exerts on the pin, and that's shown there. Then there's another force on the pin from beam 2, and finally there's the external load, which we're going to pretend was applied right at the pin. We finish this up by drawing beam 2. There is the force acting on the beam from the pin, and notice that's equal and opposite to the force acting on the pin from the beam. The assumptions we've made to draw these pictures are that there's no friction between the pin and the beams. The beams themselves are not interacting. They only interact through the pin. All forces are transmitted through the pin. Beam 1 and the pin interact, beam 2 and the pin interact, and the external load acts on the pin. There's two things that we need to understand to continue with the analysis. One, if the truss is in equilibrium, in other words not accelerating, then all forces acting on a single pin must sum to 0, the horizontal forces and the vertical forces. Otherwise the pin would accelerate. Also, beams only have force acting at each end. There's no torques acting on the end of the beams due to the frictionless pin. Remember, the way these are connected together, they're not welded. They're simply a hole and a pin pushed through. These are called two-force members. It makes the analysis very simple, although it's not really how truss structures are ultimately built. Like the pin, if the truss is in equilibrium, the total force acting on a beam must be 0, and also there can't be any twisting torque acting on the beam. Let's go over these both in more detail. How about the force balance on the pin? Well, let's draw a free body diagram of a given pin. For example, assume that 4 beam members are attached to it. Each beam is exerting a force on the pin. Here I've drawn them in the directions that those forces act. Recall that forces are vectors. They have a magnitude as well as a direction. And I can decompose this force along alternate directions and replace a single force with an equivalent system of 2 forces. Here I'm decomposing the yellow vector, representing the force F, into 2 vectors, a horizontal force and a vertical force. That force system is equivalent to the yellow force F. Obviously, trigonometry helps me determine the horizontal component of the yellow vector as well as the vertical component of the yellow vector. Next, we can sum the forces acting on a pin in both the horizontal and vertical directions. Like I mentioned earlier, for the pin to be in equilibrium, in other words not accelerating, the forces must sum to 0 in any direction. For this diagram up here, let's measure theta from that horizontal fixed line in space. There's a theta 1 measuring the angle between this horizontal line and the action of F1, a theta 2 between the horizontal line and the action of F2, and so on. If I use trigonometry, the horizontal forces all involve cosines of the corresponding thetas. They must add to 0, while the vertical forces all involve sines of the corresponding angles, and again, they must sum to 0 for equilibrium. Each pin must be in a force balance, and that will give us two equations, the horizontal forces acting on the pin and the vertical forces acting on a pin. What about the beams? Each beam has a force acting on each end from the pin that it's in contact with. So there's a single force on the end of each beam. Here I've drawn a beam with a force acting at its left end from the pin that's there, and a force acting on the right end from the pin that's there. If the situation was as I've depicted here, there's a force imbalance and the beam would accelerate in the downward direction. So these forces actually must be equal and opposite. There, I've drawn them equal and opposite now. But in this case, the force is balanced, but the beam would rotate. There's a torque acting on this beam, and therefore this is not in equilibrium as well. So these forces must be along the beam. And this picture depicts the only possible loading of a two-force member under equilibrium. The forces are equal and opposite and along the beam. Here I've drawn it as though the force is directed outward, the beam is in tension. Since these are beams, the force could also be directed inwards for a compressive load. Now we want to do the analysis. Here's our truss structure. The geometry is fixed. The load is specified. How do we determine the force in each beam? Let's let Ti be the force in beam member Bi. The next step is to simply draw a free body diagram of each pin involving these unknown forces, whose direction we know based on the geometry of the truss structure. Remember that force Ti always acts along the beam. Therefore, T2 is acting on the pins that beam 2 connects, and it acts along the beam direction. Repeating this for each one of the members gives a free body diagram of every pin, as well as a clear idea of what forces are being imposed on the wall itself. Now let's drill in and look at one of these pins. We're going to look at this one. I'm just going to erase everything else, keeping that pin exactly where it is. It has three forces acting on it, and we'll use the angle phi to denote these angles. There's a phi 3, a phi 5, and a phi 6. Again, those are completely determined from the geometry of the truss structure and are thought of as known. Let's do the force balance in the horizontal direction. We know that will manifest itself as cosines of all the angles. T3 times the cosine plus T5 times the cosine plus T6 times the cosine must add to 0. In the vertical direction, we have the same thing, except the sine plays a role. These are the two equations we know to be true concerning the equilibrium of this pin. Now let's focus on this pin. Let's specify angles. I've drawn theta 1 and theta 2. There's also a theta 5 and a theta 4, all referenced from horizontal. Some forces on this pin in the horizontal direction, that turns into cosines. Similarly, summing forces in the vertical direction manifests itself as sines. Those are precisely the two things we know about this pin being in equilibrium. Finally, let's do this pin that has the external load acting on it. Use psi2 and psi3 to denote these angles. I'm going to assume that P is acting vertically down. In the horizontal direction, we get cosines involving T2 and T3, and in the vertical direction, we get sines as well as the negative P because P is acting in the downward direction. Like before, these are the two equations which characterize that this pin is in equilibrium. Let's assemble all of the equations. For each pin, there were two equations, horizontal and vertical equilibrium. And there they are. These zeros on the right-hand side are really the requirement that there's no force imbalance on any one of the pins. The first two were horizontal and vertical for one of the pins, the next two were horizontal and vertical for another pin, and the last two were horizontal and vertical for the third pin. In the diet problem, we asked what I'll call a simple forward question. If I eat this much of these foods, how much protein and calories do I consume? For this truss problem, an analogous question would be, if these are the forces in the beams, what will the force imbalance be at each pin, horizontally and vertically? Well, that's not the question we want to answer. We want to pose and answer the inverse question. Given P, what are the correct values of the T's, T1 through T6, so that there is no force imbalance at any pin? We want to solve these equations, 6 equations with 6 unknowns, and determine the values of T1 through T6 that make it true. It would also be nice if we can convince ourselves that there's only one set of values of T1 through T6 that make it true, that there's one unique solution. I'm going to rewrite the equations including every T in every equation with a coefficient of 0 in front of it if that's the case. Now the equations look like this. It's a nice regular pattern looking of equations. Each equation involves all the T's, and there are 6 equations. The right-hand side of the equations is not 0. I've moved the known force P to the right-hand side. As we mentioned, if the geometry is fixed, then all the psi, phi, and theta are known, and the external load is known, P, then this is 6 equations and 6 unknowns, and we need to learn a strategy to how to solve these.